Hello, virtual CCGrid. It's an honor to be here. My name is Michael Murphy. I am a PhD student at the University of Tromsø, aka the Arctic University of Norway. I'm here to tell you about our experiences building and deploying wireless sensor nodes for the Arctic tundra. This is an experience paper. We built and deployed a real system of 10 sensor nodes in the Arctic tundra. This is a very simple and early prototype, so it's not necessarily mind-blowing technology, but it's an interesting and challenging environment. And challenges we did have. So we are reporting on those issues and the lessons we learned from them. I want to start by giving you a little background about the Arctic, get into describing the prototype, and then the deployment, and then the lessons learned. So let's get started. As I mentioned, I am a PhD student at the University of Tromsø, also known as the Arctic University of Norway. We are based in Tromsø, Norway, in the Arctic Circle, way up at the top of the European continent here. And we are in a good place to study the Arctic tundra. And it's important to study the Arctic tundra because the Arctic is the front line of climate change. The Arctic is the part of the world that is warming the fastest, and the tundra is the biome that is changing the fastest. We are also affiliated with an organization called CO2, the Climate Ecological Observatory for Arctic Tundra. This is a long-term program, joint program of several research organizations here in Norway to study the climate and ecology of the tundra, specifically for this purpose of understanding climate change. Part of what CO2 is doing is developing technology for sensing in the tundra because it is difficult to collect data in the tundra. Manual data collection is tough, and technological observations on the ground are tough because there's not so much infrastructure there. It's a resource challenged environment. There's very little energy, little communications infrastructure, and little transportation. So the ubiquitous connectivity that's fueling the IoT boom just isn't here. So we need to do something else. So that's kind of the core problem, is that we want to do more automated data collection, but we don't have the infrastructure that we need to do it. One thing that CO2 is doing is these small rodent camera traps. These rodents live like lemmings and voles. They live under the snow in the winter, which makes them pretty much impossible to study unless you have a camera box. We put these out where we suspect the rodents live, and there's a little hole where they can crawl in, camera in the roof to observe them. So we're actually getting data about these rodents from under the snow for the first time, and that's exciting. These cameras are a commercial traffic camera. They're simple, they're rugged, they last for a year on batteries, but there is no communication. So if you want to get your data, you have to hike out there and pick up the SD card. So what if we wanted to have devices that have communication capabilities? Well, that requires more energy, of course. So what are you going to do? Bigger backpack is more to carry. Again, we're on foot for the last mile here. Sun is plentiful in the summertime during the midnight sun, but in the winter the sun literally doesn't rise here. So solar is not an option. There's plenty of wind, but we're buried under meters of snow out in the tundra. So maybe you're thinking, well, just put the windmill on a mast. Well, we're talking a couple meters high for a mast here, so that's added weight, added complexity, and this is a pristine natural landscape. We don't want masts all over the place, and in parks it's specifically prohibited. So the easy solutions are not so easy. And again, communication infrastructure is lacking. There is some LTE in some points, maybe hilltops, but it's tough, not much coverage. If you're going to use satellite, that's more energy and probably more costly. Satellite is not cheap. I guess you could just boost signals, but that requires more power. So our research goal here is to kind of find ways to work within these constraints and overcome these challenges. We want to create a distributed cyber-physical system for observing the tundra, so we want to create a distributed Arctic observatory. So let's get into the architecture of what we think this might look like. We are picturing a distributed Arctic observatory made up of many smart autonomous observation units, smart sensors that we call observation units. And we've identified 8 core kind of abstract components that these need to have. An observation unit should, of course, observe the environment around it, the external state. That's what it's there to do. It should store the data until it can be collected or sent somewhere. It should use any and all available connectivity to exchange data, be that an LTE connection to a backhaul network, a Wi-Fi connection to your neighbor to relay maybe closer to a backhaul network, maybe Bluetooth to a phone on someone who's skiing by, anything and everything. We want to use it. And we're thinking, each unit is collecting its own data, but this data is part of a larger data set. And the data is going to be replicated and relayed and transported around the network. And we want a way to track that while still kind of keeping a perspective of the data set as a whole, some kind of data abstraction for managing this data as it flows around the network. Of course, any device is going to need some kind of runtime to manage the other components. It should also be able to run any kind of mission-specific functionality, be that on-device analytics or compression or what have you. It should also be able to download and apply its own software updates. Of course, we can't reach these things easily, so remote updates are essential. And in addition to observing the external state around it, it should be able to observe its own internal state. So debug logs or temperature, battery life, things like this. So the actual simplified application that we built is a companion to the cameras that I mentioned earlier. These boxes have a hollow spot in the wall where we can add an additional sensor to pick up, to observe things that the camera cannot. In this case, carbon dioxide measurements. We want to know what these animals are breathing. Is ice on the snow affecting gas exchange? So we have a CO2 sensor on these things. That's the external state they're going to observe. As for connectivity, for now we're just using LTE if we can find it. And then the data abstraction is simply to push and pull data from a central server for now. But once on the server, we put it into a version control system, which lets us keep the data organized and lets us easily make replicas for backup or to download to our own machine or for analysis or what have you. And it's easy to push updates around. The actual implementation, what we actually built, you see here. This is the CO2 Observation Unit. The sensor is under this little hood. These are based on a PyCom PhiPi microcontroller, which includes several different radio technologies, Wi-Fi, Bluetooth, LoRa, and Sigfox, in addition to the LTE. For now, we're just using LTE, but we hope to add the additional technologies as we go. For storage, we just use an SD card. The runtime is a simple task runner written in MicroPython. The device runs MicroPython. Updates involve installing new MicroPython code. And in terms of internal state, it's pretty simple for now, just keeping an error log and recording the LTE signal when it tries to connect. There's no additional mission-specific analytics or anything for now. That's for later. So the deployment, we actually deployed 10 of these things in the Varanger Peninsula and the Tundra landscape there. There is a cluster of 12 co-op camera boxes on a hill called Reinhaugen. We deployed 10 OUs into 12 of the camera boxes. We chose this cluster because it seemed like it would be the ones with the best LTE reception. The actual reception was not as great as we had hoped. But so this is a timeline of the contact. Each horizontal line represents an OU in a box, and the blue ticks represent a day where it managed to make contact. And when you see a solid bar, that means that it made contact every day. Don't have time to go into all of the details, but a couple things that you'll notice is that 2 of the slots are empty. Like I said, we only deployed 10 out of the 12 boxes, and that was a storage issue. Actually, in transit, some of these units they were jostled in such a way that the SD cards came out of their sockets and then got stuck on some ridges internally and ended up snapping in half. So we lost a couple of units that way. Once we deployed, you can see here on the left, there was some communication while they were in transit. And then once we actually deployed them, there was no communication for a month. This is a connectivity issue. There was just one little blip where one unit managed to make a connection briefly before it was cut off. We managed to fix that, and then you see the units operating mostly normally. But another thing you'll notice is that they didn't quite make it. None of them made it to the end. They all peter out eventually. And this was a storage issue, and I'll talk more about that as we get into the lessons learned, which we are getting to now. I want to break this down by component. So let's start with the runtime. The runtime was kind of the first where this is where one of the first big problems popped up, or unexpected problems popped up. When we were out there in the field, we had a self-test that we programmed into these units that gave feedback through an LED. And it checks hardware, it checks the sensors, and then does a quick test of LTE. And what was happening in the field was that the self-test would start and it would never stop. It would just repeat. When it got to the LTE part, it would stall, and then it would reset, and then it would do the self-test all over again. So we had to figure out how to break this loop in the field. The reason that this happened has to do with the fact that the simple task runner that we wrote doesn't use multi-threading because the MicroPython threading libraries are still experimental at this point, so we didn't use them. We just expected the task to either complete successfully or to throw an exception. As a last resort, if something stalls, we have a Watchdog Terminal which resets the unit. This was okay in the lab, and we didn't see any place where it could stall because we put a 1-second timeout on the socket for that LTE test. Well, the surprise was there was a place that could stall. Inside one of the libraries that we used, there was a DNS hostname lookup that is done before applying the timeout to the socket. So, surprise, there is a place that it could stall. So what was happening is if the DNS packet is lost, the Watchdog, it stalls, the Watchdog fires, the unit resets, the test repeats. So in the field, we actually had to improvise by pushing the SIM card out of socket a little bit so that the LTE test failed with a failure of missing SIM card, and then the unit finished the test and went into its normal mode of operation. And then we could very carefully push the SIM card back into socket while the unit was back to sleep. So, I mean, the lessons learned is that, there's always going to be surprises, and you really need to go out there and test to do this. I mean, we could have tested all the time in the lab and we probably wouldn't have noticed this. So, I think that's the value of doing experiments like this. You actually have to go out there. And so another lesson is that you kind of have to know what your libraries are doing. You have to kind of understand, a little bit below the level of abstraction that you're working with, so you don't get surprised by things like this. But the real lesson is that there is a need for preemptive multitasking, even in such a simple system. If we had preemptive multitasking, we could have put this task in a thread and monitored it. And if the task went on too long, then we could have just killed the task rather than having to rely on this brute force watchdog timer. Let's move on to lessons in storage. And this is a big one, because what happened is that if the file system gets corrupted, it led to a complete failure of the observation unit. And this happened to all but one of the units. And this is why you see in the timeline that none of them make it to July. The factor here is that the SD card is a fat file system, which is sensitive to dirty unmounts. It has to be unmounted cleanly. And so there's a risk of corruption if the watchdog forces a reset before we unmount everything. And there's a risk of a watchdog during the networking phase. And so what happens then, the surprise is once the file system is corrupted, if the way it fails is by stalling when you try to write to a file. It doesn't throw an error, it just stalls. So this led to a loop where once the file system got corrupted, then it would stall. And then that would lead to a watchdog reset, which would lead to a crash recovery routine. And what does the crash recovery routine do? Well, it tries to write the error to a log, which causes another stall, which causes another reset. And then so the observation units just got trapped in a loop of trying to record the error that was happening to them until they just ran their batteries down and died. And so that was a disaster. And it was, partially because of the file system. It's easy to forget with the modern file systems that we have on most of our systems that these removable drives and things still use simple file systems like FAT. And there is work on fail-safe file systems for small devices like this, such as little FS. And at this time, little FS is supported on the 5Pi for the flash memory of the 5Pi itself, but not on an SD card, which leads us to want to use replication. So replicate inside, write the data to the flash memory first, and then replicate it to the SD card. And replication is good because storage can still fail physically. Like we had the problem where the SD card's literally broke in half. So connectivity, the big issue was antenna placement. It turns out that the way that we placed our antennas at first that seemed natural actually attenuated the signal by about 20 decibels. In the lab, we didn't notice that because the baseline signal was high. But out in the field, it was a disaster, and that's why we had lost contact between August and September. I don't remember if I mentioned, but this is from summer of 2019 to summer of 2020. And so we had to actually go back out there and fix the antennas. And then once we did, we got more normal contact. So, lesson learned, antenna performance can be hard to predict. But something even better not better, but I'm running out of time anyway. So I will just skip this for now, get to the conclusion. And what I want to say is that the Arctic is a challenging environment. Scarce energy, scarce network, scarce infrastructure, and even simple systems like this can be difficult. But it should be a good application for research into constrained and challenged systems. And so that's what we're doing here. Thank you.